this is Mrs. Vrobel. So this is part 2 of chapter 8. We're looking at information in a chemical equation. So if you look at this slide that I have up here right now, so this is all the information we were working on with the first part. We need to know the chemical formula. Notice that any coefficient that is in front of a substance in the chemical reaction, it represents the amount. So notice that if you have a 1 in front, that means you have 1 mole of the substance. If you have a 5 in front, that means you have 5 moles of a substance. And you can use the mass to conserve mass. So notice that the propane mass plus the oxygen mass should equal the carbon dioxide and the water mass together. And that's considered conservation of mass. So if we look at the chemical equation like here, we have hydrogen, and it's being combined with fluorine. Notice that they're both gases, by the way. Together we get hydrogen fluoride. Now, notice that each of these substances on the reactant side have a coefficient of 1, and together they form 2 moles or 2 molecules of hydrogen fluoride. Okay, I'm just going to skip this slide. All right, now the next part that we need to look at is types of chemical reactions or chemical equations. So notice that with a chemical equation, there's more than one type, and we're going to pay attention to the types here. Now, where you see combination reactions, we also call that synthesis. I'm just going to put SYN. Combination reactions typically start with more than one substance and form one product. Decomposition is the opposite of combination or synthesis reactions. And then we have single displacement, and then we also have double displacement. Now, the redox reactions, we're going to ignore that for now. We're going to save that for a later chapter. Notice it's chapter 17. Okay, so the first type is combination. As I mentioned, this is synthesis reactions. And if you look at the reaction here we have 2 reactants and we only have 1 product. That's how you know you have a combination reaction. So you're always going to have more than 1 reactant, but a single product. Some examples here are metal with a nonmetal. Notice together they form a salt, and salt is sort of the generic term that we give to a metal with a nonmetal in a product. You can also have metal oxide with water, and notice we form metal hydroxide. And then lastly, you could have aluminum reacting with halogen, which forms aluminum bromide. And that's something I definitely would not do in the lab with you. That forms a solid, by the way. Okay, decomposition is the opposite of combination or synthesis reactions. So notice with decomposition, we're always talking about a single reactant and it forms 2 products. So it's the opposite of a combination reaction. And here we have metal oxides. So metal oxides, if you heat them, they typically form oxygen as their product. And notice you're left with lead 2 oxide. We also have carbonates. So calcium carbonate, when heated, will form carbon dioxide and calcium oxide. And then lastly, we could have hydrogen peroxide. So hydrogen peroxide, when it breaks down, it becomes water and oxygen. So these are all decomposition reactions. All right, the next type is single displacement. Now, single displacement, I kind of associate it with like a dance. So here we have 1 reactant, and notice in the reactant it's always by itself, okay? So that's usually a good rule of thumb with reactants. Notice that it's combining with a second reactant, and that reactant that's by itself will switch with another metal. Now, in order to understand this, I'm going to give you a special table to help you figure out whether or not this works. You need to know how reactive the two elements are that are switching places in order for this to take place. Notice it could be either a metal or a halogen that is switching place. So here's an example. Zinc with hydrochloric acid forms zinc chloride and hydrogen gas. We've actually done this in the lab before. So what you need is this table that is listed at the bottom here. And this is something that I will give you on the test. Now, the thing is, okay, if we look at sodium and iron, iron will never replace sodium, but sodium can replace iron. So always the metal on top is replacing something below it. The same thing with halogens, okay? Iodine will never replace fluorine, but fluorine can replace iodine. So here's some examples here. We have aluminum and copper 2 chloride. So aluminum is above copper, so as a result, it'll replace anything below it. And silver, notice that silver is all the way down here. It is below copper, so it'll never replace copper. Here's some more examples of single displacement reactions. So like I said, you need that table in order to figure it out. Okay, I am just going to skip through here. Okay, this is the last type of reaction that you need to know for this section. So when we're looking at double displacement, notice we have two sets of partners, and they're essentially switching with each other. So A is switching with D, and C is switching with B. How do you know? Well, these are the telltale signs. So when you're looking at a double displacement reaction, you're looking for heat. You're also looking for formation of a solid, and then lastly, a gas. So those are ways of telling whether or not you have double displacement. Here we have lead to iodide, so it forms a solid when it reacts with potassium iodine. So this is an example of a double displacement reaction. All right, and I'm going to give you a series of problems that you're going to work through to see if you can identify what type of reaction you have.